Hello students. So in the light chapter we will start lecture 4, and in this lecture we will elaborately discuss the concave and convex mirrors. So concave mirror already we have discussed a little bit in lecture 3. So we know now the curvature, center of curvature, the pole, the focus, and now we will study here where we are using these concave mirrors. So let me take first pointer. Concave mirrors are used in torches, searchlights, headlights of vehicles, and shaving mirrors to see a larger image of the face. And dentists, they are also using the concave mirrors for bigger images of any teeth. And large concave mirrors are used to focus the sunlight to produce heat in a solar furnaces. So these are the uses of concave mirrors. Now the convex mirror. So same thing, if I draw a circle here, draw a circle here. So this will be the center of the circle, and this is the midpoint. Sorry, this is the midpoint of this total curvature, right? So just a minute, I'm taking the highlighter. Right? So this one is the mirror. Now this is called pole. This is called pole, P. And this is called center of curvature. We are writing C, where C is the center of curvature. Center of curvature. Okay. Now, if we join these two lines with the center of curvature and this line is called principal axis. Okay. Now, this one is the focus. This one is the focus. Just at the, so this is the twice F length from pole to C, P to C, and P to F, that is the half of this length. So that is the F. Okay. So this is the focal length, and here the reflective surface is this one. So here, just a minute. Reflective surface is this one, and we have non-reflective surface is this one. Okay. So if the light falls on this, then you can see that if the light will fall on this, then it will be reflected from this surface, it will be reflected from this surface. So if we have some light falls on this, you can see that it will be reflected from this surface. If you have light from this, it will be reflected from this surface. Okay. So this is the reflecting surface, and light comes from this side, so it will be like this one. So this is the, by reflection of light, convex mirrors always give a virtual erect diminished image of the object kept in front of the mirror. So if you just extend these lines, you can find out where will be the image. So some image will be at this point, right? Some image will be at this point. So this is the image, and so that means always there will be some virtual erect means straight, and diminished image of the object kept in front of the mirror. Okay. Next, the use of convex mirrors. The convex mirror used in the side view mirror in vehicles to give a smaller view of the vehicles coming from behind. And they are used in shops, supermarkets, by other place where it is required to detect the burglars. So there they can use this. Convex mirrors also make the lens of sunglasses. Convex mirrors are used for magnifying glasses, telescopes. Convex mirrors are used to reflect the street light because they can reflect over the wide area. Convex mirrors are kept at the street corners to avoid the collisions. To avoid the collisions, it can be kept at the roadside. Okay. Now the total internal reflection. So we have uttered this term. Now I will give you the elaborate thing. When light passes from a denser medium to the lighter medium. Now what was the refractive index of water? 1.433, right? And what was the refractive index of air? Suppose this is air and this is water. Okay. So here that is 1.0029. Okay. So that means this is the denser medium. So if light coming from denser medium, to the lighter medium at an angle more than critical angle required for refraction, then the light reflected back to the same medium, that is the denser medium. And this phenomenon is called the total internal reflection. And light undergoing the total internal reflection also follows the ordinary law of reflection. That means if this is your theta I, the incident angle, this is your theta R, at that time according to law of reflection, theta I equals to theta R. Theta I equal to theta R, right? So when the internal reflection will be there, if the light coming from denser medium falls at the interface of denser medium to lighter medium, okay, denser medium to lighter medium. And here that critical angle, another condition is that first condition is this one, an angle of incidence that should be greater than critical angle, that should be greater than critical angle. So these two properties you have to remember. You have to remember these two properties. Now critical angle, the angle of incidence beyond which rays of light passing through a denser medium to the surface of less dense medium are no longer refracted but totally reflected. That is the critical angle. Okay. And critical angle, this is the inverse function of critical angle. I am writing here critical angle. This equals to inverse function of diffractive index and incident index. So here this one is the sine inverse of refractive index to the incident index. Okay, this is the critical angle. And the critical angle is the angle of incidence corresponding to the angle of refraction of 90 degree. Okay, so here I am writing this thing so that you can remember this thing. So critical angle is the angle of incidence corresponding to the angle of refraction of 90 degree. Clear? Now the total internal reflection we are using in fiber optic communication. Okay. So here the total internal reflection that we are using the fiber. So fiber is, I am drawing one fiber. This is a coaxial cable. this type of, made up of generally glass material, and is a piping light of in curved path it will be, and the light directed down a narrow fiber here from any source. Light is penetrating in this from any source, then it will reflect it to this surface, then it will reflect it from this surface. These are the glass surface. Okay, then it will reflect it to this surface, then it will reflect it to this one, then it will reflect it to this, then it will reflect it to this, then it will reflect it to this, and it will be going outside. So that means here the total internal reflection will be applied. The light directed down a narrow fiber of glass or plastic repeatedly reflects from the fiber here interferes at an angle larger than the critical angle. So this is the optical fiber communication, and this one is the optical fiber, and this is one type of coaxial cable, or it is the cable for optical communication. Here what happens, our sound that will be traveled through the optics, that means that will be converted to the light energy. Then the light energy, first it will be converted, the sound energy will be converted into the electrical energy. Then electrical energy that will be converted into light energy. And then light energy that will travel through this optical fiber cable, and then it will be reached to the some transmitter. Suppose transmitter means, suppose I am sending the signal to any person, so that is the transmitter. Now you can ask me one question, ma'am, why the light? We are converting a lot of things we are doing, because nowadays you require more speedy communication, right? So light is, the speed of the light is the highest speed, that is 3 into 10 to the power 8 meter per second. So due to this advantage, we are using the light as the source of energy, or the of a sound wave. Okay, and optical fibers that can transmit the light over long distance without any loss of intensity. So first thing is the speed of light, that is very high, highest speed of light, and this is one. This is number two, transmit light over the long distance without any loss of intensity. Sequences of light pulses are used to transmit information through an optical fiber network with the help of this total internal reflection. And the third is, we are using total internal reflection here, so the loss will be more less. Another thing, we are using this thing in the endoscopy. So in time of medical instruments also, we are using total internal reflection of the light. In case of our optical fiber communication, we are using, as well as we are using for endoscopy. So for endoscopy also, they are inserting one optical fiber inside our internal organ, and then they are seeing what is the defect or what is the problem you have. So these medical instruments like endoscopes, they are using the total internal reflection of the light. Okay. Next, the use of reflection. Reflection is used in periscopes to view advancing enemies on the battlefield from a safe position. From a safe position. So we are using periscope. We are using periscope here. Now, periscope, this was an American live video streaming. Okay. So periscope, here you can see that a periscope is the optical instrument that uses a system of prisms and lenses or mirrors to reflect the image through a tube. Light from a distant object strikes the top mirror and is then reflected at an angle of 90 degrees down to periscope tube. So here the periscope, that is actually where to do, yes, this is the place I can draw one mirror here, okay, and another mirror will be here. So light will come and falls on this mirror, then it will be falls on this, and then it will be going. So from this, if I keep my eye here, from this place I can see whatever the object you have here. So I can see the enemies. So this is the main use of the reflection. We are using the reflection here. So this is the mirror A and this is the mirror B. So this one is the main phenomenon of the periscope. And reflection is the reason why we see the objects, because we see the wall, we see the table, chair, everything due to the reflection. Whatever it may be regular reflection, but we can see. Reflection helps medical diagnosis, optical communication. Light and sound both follow the law of reflection, both being waves. Law of reflection for sound and light, we can measure the distance accurately to objects. Now, what you know, the light speed that equal to 3 into 10 to the power 8 meter per second, right? Suppose one light is coming after 2 seconds, that means you can find out where is the distance. So you can find out that is 3 into 10 to the power 8 into 2, that is 6 into 10 to the power 8 meter. The if light is coming, that means it is at the distance of this much. So we can find out what is the distance. And another thing is very important, that is the echo of sound. Reflection is the reason why we hear the echo of sound. And by hearing the echo of sound, we can find out where is the position, where is the position of the object also. Okay. Echo, you know, if you are uttering, suppose B, so you can hear in the mountain area whenever you are going to visit to for your tour purpose. So you just utter anything, your name also, you can hear that, or you it has been like that. Some the mountain is also uttering your name, and you can hear that thing. Okay. So suppose reflection, so reflection, so several times you can see that, you can hear that thing. So that is the echo. So echo of sound, this is also the reflection. Fine. Now here we have to choose the correct option. Correct option, what is the dimension of the object as compared to the wavelength of propagating wave when reflection occurs? So here the option A, this is large. Now reflection, I am writing the reason, occurs when a propagating electromagnetic wave impinges upon an object which has very large dimensions when compared to the wavelength of the propagation wave. Reflection occurs from the surface of the earth and from buildings and walls. Okay, we'll go to the next question. Next question. Choose the correct answer. What is the case of reflection in the course of second medium being a perfect dielectric? So here, loss of energy during absorption, total energy reflected back to the first medium, no loss of energy in absorption. This is the correct answer. Now, there is no loss of energy in absorption if the plane wave is incident on a perfect dielectric, part of the energy is transmitted, into the second medium and part of the energy is reflected back into the first medium. Okay. Next question, state true or false. The angle of incidence is equal to angle of deflection for perfect reflection. Yes, it is true. According to law of reflection. Right? Next, if child crawls towards a mirror at the rate of 0.2 meter per second, then at what speed the child and the image will come close to each other? So, in 1 second, the child comes closer to the mirror by 0.2 meters. Now, in the same second, the image comes closer to the mirror by 0.2 meters. Right? You can test it. Don't crawl, but if you are coming towards the mirror, that you can test this one also. Now the relative distance between the child and the image is reduced by 0.4 meters 0.4 meters in 1 second. Hence, the speed of child and image will come close to each other is 0.4 meter per second. Okay. State the second law of reflection. The second law of reflection states that the incident ray, the normal to the surface at the point of incidence and the reflected ray all lie in the same plane. Okay. Now image formation in plane mirror. Image formation in plane mirror. So the image formation, let me change the pointer color first. The image formed by the plane mirror is always virtual, erect, and the object and image are equidistant from the mirror. The image formed in a plane mirror undergoes lateral inversion. Right? Whenever you are seeing yourself in the mirror, what you can see, your left hand, that is related to the right hand in the image. Right? So that is called the lateral inversion. Okay? That is called the lateral inversion. And whenever you are just in front of this person, so Mr. Bean, suppose, so he is in front of the mirror, you can see that the image, that is the image, whatever you can see, that is the virtual image. This is the virtual image, because you can see that this distance, if you are this d distance from the mirror, so you can see that your image, that is also at the d distance. But is it possible the mirror, after that, we suppose the mirror is attached to the wall. So beyond the wall you are there. That is not possible. That's why it is the virtual one. So the image formation in a plane mirror, that is virtual always and erect. That means whatever you have, there will be no bending, that is erect. And this is virtual and erect image you can see, and both the images are equidistant. Both the images are image and the equidistant. That means if you are standing the distance from this mirror, then the image will be formed at a d distance from the mirror. So that is this equidistant. They are equidistant. This is the real person and this is the image of Mr. Bean. Okay. So these two will be in a same distance. Now the difference between the real and the virtual image. A real image is formed by the actual convergence of the light rays. Now, what is the convergence? So here, suppose we have this is one type of mirror. Now, the parallel lines of rays, these are coming and reflected back here. So at this point, suppose the image is this one. So at this point, you can see that this point, the image will be created. So this is the real image and this is called convergence. That means all the light rays that will meet at one point, this is called convergence. Now in optics, a virtual image is an image formed when the outgoing rays from a point on the object always diverge. And what you can see in the other form that you have seen already, that suppose this is the mirror. Now these parallel lines, this will be reflected. These parallel lines are the light rays coming from one object. Now you can see that if you join these two lines, you can see that there will be image here. So this is the virtual image. This is the virtual image. Here the virtual image is an image formed when outgoing rays from a point on an object always diverge. Here it is diverging and here it is converging. So the image appears to be located at the point of apparent divergence. And from this you can see that these are diverging. So this point is the virtual image. Now because the rays never really converge, a virtual image cannot be projected on its screen. the virtual image cannot be projected on a screen. Now the multiple reflections. So two mirrors inclined to each other are give the multiple images due to the multiple reflections. And this thing actually it has been used in so many movies also, and you can see somewhere if you are going to Science City or this type of area, and there you can see that there are multiple images. The ball is one, but because there are this is the one mirror, this is the one mirror, and this is another mirror, this is another mirror you have. So if you are keeping any ball here, you can see one image here, another image here. So multiple images you can see here. And if you are in a place where you have surrounded all the walls, that is all the walls, in all the walls you have all the mirrors, so you can see that there is you can see a multiple image of yourself. So when an object is kept between two parallel plane mirrors, infinite images are formed. Two parallel plane mirrors if you are keeping, then infinite images will be formed. Now the calculation of total number of images. Calculation of total number of images. So till now whatever we have studied, that we know. Now the multiple images, how it can be produced. Okay. So number of images formed by plane mirror is given by n equals to 360 degree divided by theta minus 1. And theta is the angle between the two mirrors. Okay, theta is the angle between the two mirrors, and 360 degree, because you know that the total plane, that is the 360 degree, right? So if the mirrors you are keeping into the mirrors you are keeping, suppose this is the mirror, and this is another mirror you have here, and this angle is the theta. So n is the number of images. N is the number of images. So n equals to 360 degree minus 1 divided by theta. So this one is the total number of images. Okay. Next, the dispersion. Dispersion of the light. This is very, very important because we see the rainbow, and if dispersion, the splitting of the light into its components, that colors, that is called the dispersion, and main example is the rainbow. Here you can see that this white light, this comes to this here, the water drop, and then it will be dispersed. So we will see that thing, how it will be dispersed. So rainbow, these are not beautiful. Have you ever wondered how a rainbow is created? So here it is simple physical phenomenon of dispersion of light. So let me write the answer. It is due to dispersion of white light. Dispersion of white light. Okay. Splitting of white light into 7 constituent colors when passed through the prism, where prism is an optical element which is transparent with flat polished surfaces that refract light and change in the direction of propagation of light when passed through a different medium is called refraction of light. Okay, refraction of light. Next, what is dispersion of light? When white light is passed through a glass prism, it splits into its spectrum of colors in order to violet, indigo according to the wavelength, okay, blue, green, yellow, orange and red, and this process of white light, splitting into its constituent colors is termed as dispersion. And here, next question. This is the last question for today. In optics, what is prism? A prism is defined as a transparent solid body that has three rectangular lateral surfaces and two triangular faces that are inclined at an angle. The angle at which the surfaces are inclined is known as the angle of prism, and it is also known as refracting angle. The other important term in the prism is the angle of deviation in prism. It is defined as the angle between the incident ray and the emergent ray. Okay. So this much for today. Thank you. Thank you all.